Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 30th, 2026, just under a week ago. It introduces a new framework called MAPPA that fine-tunes multi-agent systems using per-action process rewards, improving success rates on complex data analysis tasks by nearly 17 percentage points. The paper is titled, Scaling Multi-Agent Systems with Process Rewards. And as we'll see later, the way this method handles credit assignment without ground truth labels is really impressive. Figure 1 illustrates the architectural philosophy behind this work. At the top, a traditional single-agent model attempts to handle multiple diverse tasks alone, which effectively limits its ability to specialize. On the left, we see how Mixture of Experts architectures address this by assigning specialized expert blocks to different tasks. The authors extend this logic to the right side, where the multi-agent system scales by employing separate large language models for each role, ensuring that improving one agent's performance doesn't degrade another's. So, moving from the broad structure to the mechanics, Figure 2 maps out the agent execution loop. On the left, inputs like system prompts and environment states feed into the agent to generate an action. Crucially, look at the central red section labeled Coach Evaluation. Instead of waiting for the end of the task, an external language model acts as a coach, reviewing the agent's output, and any tool execution results immediately. This generates a reward signal that gets stored in the trajectory data shown at the bottom, which is then used to update the model. While Figure 3 reveals how differently models adapt during training, the top left panel tracks the code executor's tool usage. The orange line for the larger QN34B model shoots up to 80%, showing it learns to leverage tools, while the blue line for the smaller model stays flat. In the other charts, like the response length graphs, the orange lines drop significantly. This implies the larger model becomes more concise and efficient, while the smaller model's behavior remains static. Alright, while Figure 3 showed how their behaviors diverged, Table 1 now quantifies the actual performance gains on math competitions. The left column details results for the smaller 1.5 billion parameter model. On the easier AMC dataset in the top section, it achieves a massive jump of over 17 percentage points. However, looking at the bottom section for the harder AIM problems, its improvement is much more modest at just 5 points. In contrast, the larger QN34B model in the right column sees its biggest gain on the hard task, improving by 17.5 points on AME. Okay, moving from math problems to data science tasks, Figure 5 tracks the training dynamics on the DS Bench dataset over 84 steps. The left column displays metrics for classification tasks. Notice how both the success rate and accuracy peak early, around step 48, and then actually start to degrade. In contrast, the right column shows regression performance. While the success rate up top varies, look at the bottom right panel for the root mean square error. It continues to drop, reaching its best value at the very last step, which implies the system eventually specializes in regression at the expense of classification. Well, to understand the system behind those results, Figure 4 maps out the 3-agent pipeline for data science tasks. The process starts on the left with the data engineer, which ingests raw CSV files to handle pre-processing and feature engineering. Next, the modeler in the center uses those outputs to select algorithms and train the model. Finally, the analyst on the right generates the predictions. Crucially, they coordinate via the shared file workspace at the bottom, which allows the coach to track file dependencies and assign credit accurately. So, having seen the pipeline in Figure 4 and the trends in Figure 5, Table 2 now provides the exact numbers for that specialization phenomenon. The middle columns highlight Epoch 11, which represents the model's peak performance. Here, the total success rate jumps by nearly 17 percentage points, with strong gains across both classification and regression. However, the rightmost columns for Epoch 21 reveal the cost of overtraining. While classification success falls back to its baseline, regression performance remains high, and the quality metrics in the lower rows continue to improve. This confirms that the system eventually sacrifices broad competence to specialize in the tasks it finds easier to optimize. Wrapping up, 2 takeaways stand out. First, using a language model coach for per-action rewards effectively solves the credit assignment problem, enabling true agent specialization. Second, this demonstrates that we can scale complex systems without needing ground truth labels for every step, which moves us closer to self-improving autonomous swarms. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.